We want to use set builder notation and logical equivalences to show that the set operation, the union of the intersection of A and B and the intersection of A and the complement of B is equivalent to A. Let's get started. So first we're going to go ahead and use set builder notation to write, I think that's enough. We can say that the set of X such that, and here we're going to write our condition. So we're just going to translate this using what we understand about intersections, unions, and complements. So we know that the intersection of A and B is equivalent to X belongs to A and X belongs to B. And then this union is equivalent to a disjunction or symbol. And then let's go ahead and work on this one. This is equivalent to X belongs to A and X belongs to B hat, or the complement of B. As you guys know, we can rewrite the complement of B, X belongs to the complement of B, to X does not belong to B. And let's just get rid of the complement sign there. And similarly, we can write X does not belong to B is it is not the case that X belongs to B. So I'm going to rewrite it like that. It is not the case, and that is the negation, it is not symbol, that X belongs to B. And this is most appropriate for our case. So now that we have this, I'm going to distribute this proposition across these two propositions. So we know that if we have one proposition, let's say this is our proposition P, we can distribute it across two propositions Q and R. We already know this, and that's exactly what we're going to do. So once we distribute it, we get an equivalence that is the set of all X such that X belongs to A and X belongs to B, or, and now we can distribute. So let's say X does not belong to A for the first one, and write the and symbol, and then we can distribute it across here. So again, we write the set of X such that, or we write X belongs to A and X belongs to B, and then we are going to distribute this time across this one. It is not the case that X belongs to B. And here we have our distribution. Make a small one here. So these two propositions are equivalent. This proposition is equivalent to this proposition. So now let's go ahead and define it further. We can rewrite this single proposition as simply being X belongs to A. In other words, X belongs to A and X belongs to B, or X belongs to A, is equivalent to simply X belongs to A. Now, if you remember your propositional equivalence from propositional logic, you know that if we have some P and some Q, or P, then this is going to be equivalent to P. And that is the exact same type of pattern that we have here. Some P and some Q, or that same P. And that is going to be equivalent to that P. Alright, now that we have this part, let's work on the right side of this conjunction. So we're going to drop down our conjunction symbol, and we're going to work on this part. So I'm going to distribute this proposition across this one and this one. So we're going to get the negation of X belongs to B, or, and then distribute it across this one first, X belongs to A. And then, and, again, we're going to distribute the negation of X belongs to B, or, and now this time across this one, X belongs to B. So now we have, I'm going to draw our set symbol, the set of all X such that X belongs to A, and the compound proposition, it is not the case that X belongs to B or X belongs to A, and it is not the case that X belongs to B or X belongs to B. So we can further work with our propositional equivalences to come to another equivalence. We know that whenever we have some P and then the negation of that P in a disjunction symbol, we have P or not P. This is X is in B or X is not in B. Anytime you have a P or not P, that is simply going to be equivalent to true. because both options are satisfied. So we're going to drop this down. We're going to have here again the set of all x such that, and then first I'm going to just drop this one down. X belongs to A, and then we're going to work again here. So I'm going to write, it is not the case that x belongs to B or x belongs to A. And then I'm going to rewrite this one. As we said, this is going to be equivalent to true. So we're just going to rewrite this one and true. So now let's think about what other equivalences we could come to. We know that whenever we have some proposition P and true, this is going to be equivalent to P itself. So here we have this compound proposition. We could regard it as our P and true. This is going to be equivalent to just the compound proposition itself. So I'm going to again write the set of all x such that x belongs to A, and then we're going to focus on here. So this is simply going to be, it is not the case that x belongs to B or x belongs to A. So this is our proposition. And again, this is equivalent to this, which is equivalent to this, which is equivalent to this, which is equivalent to this. So we are simply left with the set of x such that x belongs to A and the compound proposition, it is not the case that x belongs to B or x belongs to A. So one more way we can reduce this is whenever we have some proposition P and a compound proposition, some Q or P, this is going to be equivalent to P itself. So it doesn't matter if this is Q or if this is not Q, it doesn't matter. But if we have some proposition P and a disjunction that has P in it again, that is going to be equivalent to just P. So here we have some proposition x belongs to A and a disjunction with again x belongs to A. So all of this is going to be equivalent to simply x belongs to A. So we have the set of all x such that x belongs to A. And finally, we know that the set of all x such that x belongs to A is equivalent to A. That's right. Is equivalent to A. And so we have established through a set of logical equivalences using set builder notation that the union of the intersection of A and B and the intersection of A and the complement of B is equivalent to A.